In this video, let's discuss about this acidity of carboxylic acids. Yes, when we look at the acidity of carboxylic acid, here the acids, the carboxylic acids react with the sodium metal, resulting in the evolution of this hydrogen gas here. And they also react with sodium hydroxide, resulting in the formation of sodium salt of carboxylic acid, that is sodium carboxylate, and water is being formed here. So when you look at this reaction, this is similar to that of this alcohols. That means alcohols also react with sodium evolving hydrogen gas. And when we look at this sodium hydroxide reaction with sodium hydroxide, phenols also react with sodium and also sodium hydroxide, resulting in the formation of water here. So these two reactions are similar to that of the phenols, which says that now these two reactions, the carboxylic acids, this class of compounds are acids. Right, but unlike phenols do not react with sodium bicarbonate, but these carboxylic acids react with sodium bicarbonate, resulting in the formation of sodium salt of the carboxylic acid. That means sodium carboxylate, water, and carbon dioxide. But phenols do not react with sodium bicarbonate. Here, sodium hydroxide is a strong base. Sodium bicarbonate is a weak base here. So which shows that this particular reaction, which is shown only by carboxylic acids and not by phenols, shows that this is a stronger acid, because phenols react with stronger bases, which means it's a weak acid. But here carboxylic acids also react with a weak base, resulting in the formation of carbon dioxide. This carbon dioxide gas is evolved. So this test is used for the detection of the carboxyl group. So the reaction with sodium bicarbonate is used for the detection of carboxyl group. Right. Now let's look at how this dissociates in water. Carboxylic acid dissociates in water, resulting in the formation of hydronium ion and the carboxylate ion. This is a carboxylate ion, and this carboxylate ion is in resonance. These are the two resonance structures which are possible for this carboxylate ion. This is a resonance hybrid. And if you write for the above equation, the equilibrium constant KEQ, that is KEQ is nothing but here the equilibrium constant, the concentration of the products, right? It's concentration of the products by concentration of the reactants, RCOOH, right? Yeah, here K equilibrium is equal to concentration of the products by concentration of the reactants. KEQ into the concentration of water is equal to Ka. It's a new constant which is called as acid dissociation constant, which is equal to the concentration. I'm writing the rest of the reaction here, RCOO minus by RCOH. Right. So what is KEQ here? KEQ is nothing but the equilibrium constant. Right. Equilibrium constant. And Ka is the acid dissociation constant. Right. Here Ka is nothing but the acid dissociation constant. Right. Now this one Ka can be further written as minus log pKa is equal to minus of log Ka. Now this pKa can be used to show the strength of the acids. The lower the pKa, the higher the acidity, right? So pKa is inversely proportional to the acidity. So now we can express the acidity in terms of pKa now. Yes. Now let me write the pKa values of few acids here. If you take the mineral acids like HCl, the pKa value of this is -7. This is the pKa value. Right. Of trifluoroacetic acid, this is the strongest of the carboxylic acid. It's 0.23. And if you take benzoic acid, this is what is benzoic acid? Let me write the benzoic acid. Yes, this is the benzoic acid. The pKa value of this benzoic acid is 4.19. And the pKa value of acetic acid, CH3COOH, is 4.76. So these are the pKa values of carboxylic acids and the mineral acid, right? I just now said that the lower the pKa, the higher the acidity. That means it's inversely proportional to the acidity here, right? That means what does an acid mean? Acid means it's able to donate the proton. So the stronger acid means that the ease with which it can give the H plus, how easily it donates the H plus. And that means the stronger the acid, the better it is a proton donor. Yeah. Now, the stronger acids have the pK values less than 1. For example, these mineral acids like HCl, H2SO4 all have the pK values less than 1 and which have the pK values in the range of 1 to 5 are called as moderately strong acids. These are strong acids. Yes, strong acids. These are moderately strong acids, right? Moderately strong acids. Now, in the range of 5 to 15, 5 to 15 are weak acids. And above 15, pKa values above 15 are extremely weak acids. Right. This is pK values for, to determine the strength of the acids. If it is less than 1, they're strong acids. If it is in the range of 1 to 5, for example, we have this carboxylic acids are moderately strong acids. That means the carboxylic acids have lesser pKa, are weaker acids than mineral acids. In the range of 5 to 15 are weak acids, and more than 15 are extremely weak acids. For example, the alcohol, which has a pK value of 16 here, right? pK value of 16, and for phenol, it's 10. See, that means from this we can easily determine the acidity of this, right? So phenols are definitely more stronger than alcohols, and I've discussed about this, why phenols are more acidic than alcohols in my previous video. Now let's look at why carboxylic acids are better acids or stronger acids than phenols. Okay, these are the pK values of different classes of compounds. These are for the mineral acids, which are less than 1. These are for the carboxylic acids, which are in the range of 1 to 5 and 5 to 15, for example, alcohols and phenols. The phenols are 10, alcohols are extremely weak acids, more than 15. Right? Now, these are the pK values. Right now, let's understand why the carboxylic acids are more acidic than phenols. Yes. Now, just now I said we can decide the acidity of carboxylic acids or phenols based on the stability of the ions conjugate base which is being formed. Right after the donation of the proton, the conjugate base which is formed for phenols is a phenoxide ion, and for carboxylic acids, after the donation of the H plus, this is giving what? The carboxylate ion. This is a carboxylate ion, right? When we look at the stability of these two, that the more stable the corresponding ion, the more basic the as the more acidic the corresponding acid will be, right? The corresponding compound is depend upon the stability of the conjugate base which is being formed after the donation of the proton, right? This is formed from the phenol after proton is given off, right? So it depends upon what stability of the phenoxide ion or stability of the carboxylate ion. Now these can be compared based on the stability of the conjugate base which is being formed. Here, for example, if I'm taking this carboxylate ion, these are the two resonance structures which are possible for the carboxylate ion. And this is the resonance hybrid. These two are two resonance structures, and these two resonance structures, if you can see, they're equivalent here, right? These two equivalent resonance structures, right? Here, there are 5 structures which are possible, but if you look at it, they are non-equivalent resonance structures. So here, the negative charge is on the oxygen atom, rest of it is on the carbon atom. So they are non-equivalent resonance structures. Right. Here, we know that the compound which is having even though it has 5 resonance structures, since they're non-equivalent, phenoxide ion is not as stable as a carboxylate ion, because here the resonance structures are equivalent here, right? It doesn't depend on the number of the resonance structures, but it is dependent upon the equivalent or non-equivalent resonance structures here. Even though there are 2 in number, this carboxylate ion, says they're equivalent, the carboxylate ion is more stable depending upon the phenoxide ion. This is one reason. And the second reason here is, if you can look at it, the negative charge here is made by the oxygen atom, right? Negative charge is on more electronegative oxygen atom. Here, negative charge is on, if you look at it, carbon atom and the oxygen atom. So less electronegative carbon atom, right? So it is better for a more electronegative atom, that is oxygen atom, to bear a negative charge than the negative charge on the carbon atom. And the third reason is there is effective delocalization be here, because a negative charge is delocalized in between the 2 oxygen atoms here, more electronegative oxygen atoms. So effective delocalization, right? Because it is shared by 2 oxygen atoms, more electronegative oxygen atoms. Here, the negative charge is shared by 1 oxygen atom and the other one is a carbon atom, which is less electronegative. So not the delocalization is not effective here, not effective delocalization. So these are the 3 reasons why carboxylate ion is more stable than the phenoxide ion. Because here in carboxylate ion, even though there are 2 structures, resonance structures which are possible, they're equivalent. Here they're non-equivalent resonance structures, even though they are 5. And here the negative charge is delocalized on, is on more electronegative oxygen atom. Here, if you look at the structure, see the negative charge is on less electronegative carbon atom. Here there's effective delocalization because the negative charge is shared by more electronegative oxygen atoms, 2 oxygen atoms here. Here the negative charge is shared by the oxygen atom and the less electronegative carbon atom. So based on these 3 reasons, carboxylate ion is more stable than the phenoxide ion. So the corresponding compound, that is the carboxylic acid, is a better acid than a phenol. So carboxylic acids are more acidic than phenol. So what can I say here? Carboxylic acids are more acidic than phenols. These 2 reasons. Okay. So the conjugate base, same thing here. I'm sorry. Same thing here. Here 2 equivalent resonance structures. Here 5 non-equivalent resonance structures here. Here, the negative charge is effectively delocalized on 2 electronegative oxygen atoms. Here is less effectively delocalized over 1 oxygen atom and carbon atom here. Right. Now, I'm going to discuss the effect of the substituents on the acidity of carboxylic acids here. Here, how the substituents will affect the stability. Yes, the substituents will definitely affect the stability of the carboxylate ion and so the acidity of the carboxylic acids. If it, I mean, the substituent which is present on this carboxylate ion, this is a carboxylic acid, this is the carboxylic acid, right? If there is a substituent, that means I'm taking it as electron withdrawing or electron donating group. If this affects the stability of the carboxylate ion, it will definitely affect the acidity of the carboxylic ion. If it stabilizes the carboxylate ion, for example, if it is an electron withdrawing group which is present on this carboxylate ion, then it will share the negative charge on the ion, right? It will share the negative charge by its electron withdrawing capacity because it is withdrawing the electrons from the carboxylate ion, thereby stabilizing it. So it strengthens the acid. That means it increases the acidity of the acid. Whereas if electron donating groups is present, there is already a negative charge on the carboxylate ion. Thereby, if it is donating, it will increase the negative charge on the carboxylate ion more, thereby destabilizing the carboxylate anion and therefore weakens the acid. That means it decreases the acidity. So to sum up, we can say that electron withdrawing groups increases the acidity, electron donating groups decreases the acidity of the acids. Right. Now, these are few of the groups in the increasing order of the acidity, where CF3 trifluoroacetic acid, I just now said, is the strongest of the carboxylic acid. Strongest acid, carboxylic acid. Right. Then comes NO2, CN, FCl, Br, I, and finally the phenyl group. And this is the order of the acidity of the carboxylic acids. Few of the carboxylic acids are given below. Right. First comes trifluoroacetic acid, then comes NO2, CN, right. Then if you can observe, as a distance in between the acid and the halogen increases, the acidity decreases. Right. Then comes bromo here, chloro after bromo, because chlorine is more electronegative. Then again, as the distance increases, acidity is decreasing here because the inductive effect decreases here, right? Then comes benzoic acid. Then we have finally the acetic acid, and here propanoic acid, right? Now let's look at the effect of the vinyl group, how this vinyl group affects acidity of carboxylic acids. If you see, there is a resonance. This is vinyl group, CH2C. This is called as the vinyl group, and this vinyl group, when attached to this COH, that is a carboxylic acid group, there is a resonance which we can see here. Right, because of this resonance, what should happen? That means it is pumping in the electron density towards the COH group. It should decrease the acidity because it destabilizes the anion. But it will, on contrary, it should decrease, but it is increasing the acidity here, increases the acidity because of the resonance. What should happen? It should decrease the acidity, but what is happening? It increases the acidity. Why? Because if you see here, the carbon which is attached to the carboxylic acid group, this carbon is sp2 hybridized. That means if you see in acetic acid, here, this carbon which is attached to the carboxylic group is sp3 hybridized. We know that sp2 hybridized carbon atom is more electronegative. So if it is more electronegative, it will keep the shared pair of electrons towards it. That means it will attract the electrons, that means shared pair of electrons, more closer towards it, therefore donating this H plus easily here because of this difference in the hybridization of the carbon atom, which is sp2 hybridized, making it more acidic, right? So how does the acidity be affected here of the aromatic carboxylic acids? Right. Simple here. If there is a electron withdrawing group, for example, this is a benzoic acid, this is 4-nitrobenzoic acid, and it is, what is nitro? It's electron withdrawing group. Electron withdrawing group. If the electron withdrawing group is present on the aromatic ring, it will, what is happening? Electron withdrawing group increases the acidity. How? It will increase the acidity, and this is evident from the pKa values also, right? So how it is increasing the acidity means it will stabilize the carboxylate ion which is being formed. This is the carboxylate ion, right? If it is electron withdrawing groups, it will stabilize the carboxylate ion because the negative charge on this ion is shared by this nitro group, is shared by this electron withdrawing group, thereby increases the acidity. But if it is an electron donating group like methoxy group here, it will decrease the acidity because decreases acidity because it will destabilize the carboxylate ion which is being formed. This is a carboxylate ion and this is OCH3. That means it will give more electrons towards this carboxylate ion, already negatively charged, pumping in more electrons towards this ion, thereby destabilizing the ion. Therefore, this is the order of the acidity of aromatic carboxylic acids depending upon whether it is electron withdrawing or electron donating groups. Electron withdrawing groups on the ring will increase the acidity. Electron donating groups on the ring will decrease the acidity, evident from the pK values also. Yes, if you like my video, please do like, share, and subscribe my channel. And if you want any video to be made on any particular topic, please share it in the comment section. And the whole chapter has been discussed on my YouTube channel, and the details of it has been given in the description box below.